Bristol, and he's going to talk about towards paraconsistent quantum set theory.
Cool. Okay, cool. So, yeah, thank you. So I'm going to be talking about kind of two approaches to quantum theory that have been around for quite a while now, both of them in various guises. And really the kind of point of the talk is to find some nice connection between the two, because reasons I explain, I kind of always thought they looked similar in a vague kind of conceptual way. So the first one is Thomas quantum theory specifically. I'm thinking about the contravariant approach. It goes back to papers by Isham and Butterfield in the 90s, so they gave us new statement of the Cauchy-Becker theorem and all of this kind of stuff. So yeah, those people like Andreas Düring and others kind of developed this and attempted to argue that if you use Topos theory in a suitable way, you can get a kind of a nice realist reformulation of quantum theory. And specifically I'm interested in the logical aspects, so they argue that this gives you a natural intuitionistic kind of quantum logic that somehow improves on the original kind of the modular setting in various ways. So that's the kind of the first approach I'm interested in. And then the other one that's maybe been kind of less well studied, especially in recent times, is quantum set theory. So this actually goes back to Japanese mathematician Takeuchi in the 70s. What he did was he proved the existence of particular models of set theory in which the real numbers are isomorphic to particular sets of self-adjoint operators. The idea is you can kind of build models of set theory whose real numbers encode some kind of fragments of the physics of particular quantum systems. And so a few people following on, specifically in recent years, Masao Ozawa, have been trying to use this to build these models and kind of reconstruct a lot of the Hilbert space formalism kind of inside the models, specifically rather than looking at self-adjoint operators, for example, you just look at the reals inside these particular models. So to me these look kind of in a weird, vague conceptual way, like they're doing the same kind of thing in the sense that they say, all right, let's look at a quantum system, let's take its Hilbert space, and then let's use that to build some non-classical mathematical universe with its own internal logic, and then we can kind of get a new, kind of extend the formalism in various ways by doing everything inside of these kind of new universes, something vague like that. Okay, so that's kind of what I'm saying here. And the other thing on a more technical level is there are various things in each approach that have been done that the other one lacks. So if I have time, I'll talk about this at the end. And it would be nice to have some technical way of transferring the results to and from the different approaches. And I think that's kind of what we start to get at the end of the talk. So yeah, I'll just start off. I'll give a very quick sketch of what very specific bit of Thomas quantum theory and show how we can introduce a new logic that's not been studied before in there. Then I'll do a similar thing for quantum set theory. Give a very rough sketch of how you can kind of unify these things using the new logical structure, and then hopefully sketch some of the results that you can get out of this. So first of all, this is stuff by Andreas Düring and his student Sarah Cannon that they did here a couple of years ago. So quick way to present what I need. So in quantum logic, we normally take some orthomodular lattice L. For our purposes, that's always going to be a projection lattice on the Hilbert space, or some Hilbert space H. We let B of L represent the coset of Boolean subalgebras of L, so you kind of just order them by inclusion. Then you can, in a natural way, find a pre-sheaf over B of L, where you just take each Boolean subalgebra B, you just lift it up to its Stone space everywhere, so that's this omega is this pre-sheaf that we're defining. So I'm writing omega of B for the Stone space, or omega of L at B. So it just takes each Boolean subalgebra, it just gives you back the Stone space, and then on arrows it just does the usual kind of thing. You have an inclusion arrow between B and B prime, you just flip it around and you get a restriction map between the Stone spaces of B prime and B. And this is what's called the spectral pre-sheaf. So this is, the idea is, in some sense, this is some kind of new state space that takes, the idea is each Stone space is the local state space for a particular classical perspective on the system, something like that. So then the next thing you can do is if you have an element of L, so in our case this is going to be some projection operator, so A here, you can then define for any Boolean subalgebra the kind of the best approximation to A at that Boolean subalgebra. So maybe A says something about the position very precisely, and B represents a context where you already know very precisely about the momentum. So maybe you can't exactly say A in a meaningful way there, so you kind of approximate it. And the idea is this delta of A, what we call decimalization, this is the best approximation to A at B. So this is the smallest thing that you can say at B that's implied by A. That's the basic idea. And then this, for any A, this defines a presheaf of a B of L, because you just take every B and you just basically take it to this approximation. So it just gives you a projection operator at every B, and every B is just the closest thing you can say to A. Or equivalently, you can think of it as the subset of the stone space that makes that approximation true. So this is a set of all of the algebra homomorphisms that send it to the 0, 1 algebra that give this approximation the value 1. Again, the maps are just the usual thing. You just flip them around and get restriction maps. It's easy to see this is all well defined. And so this is another presheaf that we've got here. We call this delta of A underline. This is the whole presheaf that you get corresponding to A. And so by stone duality, this at any B, the set that delta of A gives you at B is a clopen subset of the stone space of B. And so you kind of generalize this and you say that any of these presheaves corresponding to A, any of these decimalization presheaves, is what you call a clopen subobject of the spectral presheaf. So it gives you a clopen subset everywhere. Now it's been shown by Andreas and Chris and others of one of the basic theorems is that this is a complete Hastings algebra under kind of natural operations. So you basically take context-wise intersections and close them under the topological operations. So we've got to think of this delta as a map that goes from the orthomodular lattice of projections, and it goes into a complete Hastings algebra. It gives you a clopen subobject for every element. And it's injective, and it's joint preserving, and monotone, and nice in various ways. And so, maybe I should say quickly, so what the interpretive move that they make in Topos quantum theory normally is they say, okay, the propositions aren't actually the projection operators, they're the clopen subobjects. That's the kind of the key interpretation move. So then, this is what Sarah and Andreas showed, okay, well, delta is a joint preserving monotone map between posets. It has an adjoint, which is meet preserving, and surjective, and this is map epsilon. The specific form won't be important now. I've never actually remembered the specific form, let's forget it. But the important thing is it's a map going back from the clopen subobjects back down to the projections. So it's, it's just the adjoint. And you can use this map to define equivalence relation on the clopen subobjects in quite a natural way. So all you do is you just say two clopen subobjects are equivalent if they are if epsilon agrees on them, basically. So if they both get sent to the same projection operator, then you say that they're equivalent. That's the basic idea. And then, so you take E as the quotient class of the clopen subobjects under this operation. So it just sends, so it's just a set of all equivalence classes of the clopens. And this is turned into a complete lattice under these kind of natural operations. You just take the meets are the same as the meets and the clopens because epsilon preserves meets, and then you define joins in terms of that. And so this is a complete lattice. Now the relevant point is that E and L are isomorphic as complete lattices. That's kind of the big result that we need, that I end up having to use. So we can represent L perfectly in terms of its lattice theoretic structure as a quotient class of the clopens. Right. Now, this is where the new stuff starts. So it's already well known that clopens form what's called a complete bi-Hastings algebra, which means you can think of them as a model both of full intuitionistic logic and of a particular form of paraconsistent logic. So this is what Andreas showed. But the paraconsistent structure has never really been looked at because it's somehow it's not very natural. I think it's hard to really do very much with it. But there's actually another paraconsistent structure which arises very naturally once you start using this epsilon. So this is this new structure that we're going to have. So specifically, you define it like this, you have some clopen subobject S. So you know you can take it by epsilon down to some projection operator, so it uses the joint map down, gives you a projection operator. Then there you just take the ortho complement, because this is a projection, we can just take the ortho complement, and then we can use delta, the Dastonization map, to take it back up to a clopen subobject. So it's like we just do this loop of adjoints, but halfway around we throw in an ortho complement. This is giving us another clopen subobject, which we're going to call S star, and this is some new notion of negation. Now we want to study, well, what's this like? This is like quite a natural thing, because it's the translation into Toppler's quantum theory of the ortho complement. So the first thing we know is this extends the isomorphism between E and L, so that they're now isomorphic as ortholattices as well as complete lattices, so the negation is being preserved by this isomorphism. The second thing is, this is where it gets weird, as well, this is now paraconsistent. So that's this little argument here, I'm not going to spell it out, but it just follows from the properties of these adjoint maps, that this star map, so this is the translation of the ortho complement, when you lift it up to the clopens, it becomes paraconsistent. So this is kind of, I don't know, I found this a bit surprising and weird, but it turns out that this is actually, it's not just any paraconsistent logic, it's quite a nice one. So specifically it has all these properties, it has law excluded middle, half of double negation, 3 of the De Morgan inequalities, and basically what this all shows is that it's a model of a very well-known paraconsistent logic called dialectical logic with quantifiers, which goes back to the 70s by people like, developed by people like Routley and Meyer and Graham Priest. And it's in paraconsistent logic, it's a very important one, what I came to learn, because if you want to do things like define set theories or real analysis of paraconsistent logic, this is a project that a lot of logicians have done in the last few years. This logic is somehow maximal in the sense of having non-trivial theories. It's very difficult to add anything more to this logic without having your set theory be trivial. So this is something that's important in paraconsistent set theory. So it's kind of quite lucky from my perspective that it models this specific logic. Okay, so now to quantum set theory. So I'm not going to go into too much into the details here. The first thing is, if you have some complete Boolean algebra B, it's a well-known set theory that you can use this to construct this model called VB, which is a set theoretic structure. It's got this recursive definition, but we don't have time to go into details. But the key point is that it doesn't matter what our choice of B is. It can be any choice of B as long as it's a complete Boolean algebra. It's a model of Fools and Euler-Frankel set theory of choice. So this is kind of a basic fact about what's known as forcing. And if you change B, you can change various properties of the model and get it to falsify various set theoretic statements or verify them. So you can get a proof of the independence of the continuum hypothesis doing this. So this is a kind of a big thing. So yes, these are Boolean valued models. Now, what Takeuchi did was he said, okay, well, let's consider the case where B is some Boolean algebra projections of commuting projections. So what he showed was, so this RB here, which is the reals inside of this model VB, where B is a Boolean algebra of projections. So what he showed is that then the reals in this model are isomorphic to all the self-adjoint operators whose spectral projections all lie in B. So it's all of if you're just looking from the perspective of B, it's all the self-adjoint operators that B can kind of talk about perfect information somehow. And these are perfectly encoded by the reals in this model. So this was kind of the Takeuchi's big famous theorem. And so what people like Ozawa and others have tried to do is they said, okay, well we got this theorem just for Boolean algebras of projections, but wouldn't it be nice if we could build a model where the reals encode not just some part of the physical structure, but the whole physical structure of the system. So the reals in these models are isomorphic, well not isomorphic, but bijective to the set of all self-adjoint operators on the whatever Hilbert space we started with. So that's the kind of the goal. And the natural way to do this is say, okay, well let's not just take some Boolean subalgebra, let's take the whole projection lattice and build this model from here. Now the problem is, of course, that then this isn't a model of any well-known set theory, because the whole projection lattice is non-distributive and horrible in various ways. So you don't get a model of a well-known set theory. But there's been really nice work done in showing, okay, so you can't get a full set theory, but this models lots of nice little fragments of ZFC, and specifically enough that you can build some nice real numbers and things like this. And then, of course, the isomorphism goes through, so, or the bit bijection, I should say, is that all the reals in this thing, when you suitably define them, they're isomorphic to the set of all self-adjoint operators on H. So you've got this set theoretic universe in some sense whose reals are the same as the self-adjoints on the Hilbert space that you started with. So that's kind of a nice idea, and then Ozawa's been using this to kind of reconstruct lots of nice kind of quantum structure inside of this model. And so I think he gave a talk last year at QPL about how you can use this to extend the Hilbert space interpretation, various things. We've got lots of papers on it. So now, the thing I want to know is, okay, well, this is the kind of the basic fundamental theory of quantum set theory. If we want to see how this relates to Topos quantum theory, we want to get something similar in Topos quantum theory. And this also has another nice motivation, is that in kind of the Topos quantum theory that's the contravariant approach, the reals are a bit of a problem because the reals that are actually used in the formalism aren't the reals in the topos that you're using. They're a bit, you've got to cook them up. So this would be nice if we could somehow have some kind of correspondence like this to give a nice notion of the reals in Topos quantum theory. So this is kind of the big idea now is, okay, so rather than studying V to the P of H, we're going to study V to the subclopens. This is kind of the key idea. I'm going to say, okay, well, can we get the same, anything like the same theorem in here? And this is motivated by the idea that in Topos quantum theory, the clopens kind of replace the projections somehow. So first off, you think, oh, well, this should be easier or somehow nicer because, well, the clopens are distributive, complete hating algebra, whatever. This is going to be a model of intuitionistic set theory. Lots of the problems will go away. It's going to be easier. So we can go ahead and try and reconstruct the Takeuchi-Ozawa proof and whatever. This is what I was trying to do this for ages. But it doesn't work really. So the basic way I try to do the proof is I just try to lift Takeuchi and Ozawa's original proof, and then use this isomorphism between E and P of H that I talked about earlier. The problem is that this isomorphism really doesn't preserve at all very much of the hating or bi-hating algebraic structure of the clopens. But we saw what it does preserve is it preserves star very nicely. So if we think of this as being equipped not with the hating algebraic structure or a co-hating algebraic structure, but with star and this corresponding structure, then the isomorphism preserves much more of the logic. And basically, so this is all in the paper, show that if you use star, then you can actually construct a version of the Takeuchi-Ozawa isomorphism. So maybe I'll come back to this in a sec. I'll just skip ahead to the statement. So I don't get the full theorem, but what we have is if you have any two, so this thing, this AB to the subclopens, this is where A and B are just normal real numbers, and this is all the things in V to the subclopens that the model thinks lie in between A and B. So these are all real numbers in the model that the model thinks lie in between A and B. And this thing on the right, BSA of HAB, this is all the bounded self-adjoints on H whose spectrum is contained in the interval AB. So what I showed is that for any A and B, these two things are bijective. So this isn't quite as good as what Takeuchi and Ozawa have in their approach, but it's close. And specifically, it pretty much allows you to do all the stuff that they use this bijection for. Namely, I haven't checked it all yet, but it lets you do a lot of the stuff. So this is kind of the best first approximation I can get. And this is only possible using this star operation. A quick caveat to just go back is that obviously now our logic is paraconsistent. So this V to the subclopens isn't a model of classical set theory either. It's going to be a model of anything. It's going to be a model of a paraconsistent set theory. So that seems like a problem, but this is something a lot of people are working on right now, and this comes back to this point of the subclopens modelling DKQ on the star. Because, so specifically Zach Weber's had a series of papers in the last few years developing a particular form of paraconsistent set theory, and it's by far the best developed one in the literature. And it's got strong non-triviality proofs. It's a very interesting theory, it seems. And there's a lot of people working on the model theory right now. And it's the underlying logic is actually DKQ, not DKW. So the subclopens we know model this logic. So insofar as this theory is ever going to be able to have algebraic valued models, our model will be a model of this theory. The idea is that's nice. Now, even if this doesn't work out and we don't get a full model of a paraconsistent set theory, it's possible to. I've recreated most of Ozawa's kind of transfer theorem schemes. So you have we know that this Vita subclopen models various fragments of ZF, and it's enough to build reals, which at least for our theorem we know we have enough there. But this is still very open, and there's still a lot of scope for things to go wrong. Okay. Alright, so a quick sketch of some of the final things that we've done. So one thing in the Topos approach that's not been done very well is things. Representing operators has always been a bit tricky in this approach, and in particular things like operator inequalities. But this is something that quantum set theory does really nicely. So I'll give a quick explanation. So if you have self-adjoint operators x and y, so I should say this section is stuff I'm working on now with Massenal and Andreas. So if you have self-adjoint operators x and y, so what we've shown is we know that we can find canonical representations of them in here, and this is basically done just the same way that Massenal used to do it in V to the P of H. So you can find canonical representations in here, and you can show, so this is the truth value that x is less than y in this model. So this is going to be a clopen subobject, this truth value. This is going to be true, maximal, exactly when x is vectorially smaller than y. So somehow we're representing the operator order on the Hilbert space in the internal logic of this set theoretic universe, which is nice, and that's the state-independent version. We can actually get a finer-grained state-dependent notion. So we know that these truth values are always clopen subobjects, so we can think about, all right, what's epsilon of this clopen subobject? This is a projection. When is psi in here? Well, this is the same thing as saying that the Dasonization of the projection onto psi is less than this truth value, so this truth value is somehow measuring the order of these operators. And that's the same as saying that the joint probability of obtaining these outcomes from successive projected measurements is, in state psi, is 0 whenever x is bigger than y, which is actually the operational meaning of what we think of x being less than y. So we have like a three-way kind of picture where we've got, this is like the quantum set theory picture, this is the Topos quantum theory picture, and this is like an operational picture. So we've got like 3 ways of representing the operator order here. So I was going to quickly mention something else, but I think I will maybe leave it there.
Any questions, comments, Chris?
Probably 2 related questions. First of all, why is it called dialectica? And second, what's the intuition? Do you have any intuition for the star? How should I think of it?
Yeah, it's called dialectical because this is something weird in the paraconsistent literature that this word came up. I'm not sure exactly what it is. I don't know if it's related to dialethic, because that's the word that they use for paraconsistent. So I don't have a good answer to that. And the intuition is just, I just think of it as being just the translation of the orthocomplement into the clopens.
Under this adjunction?
Under this adjunction. It's just that the natural way of representing that. Yeah, I also don't have a great intuition for it, to be honest. I didn't want to have to use it. It just came up very naturally in solving this problem.
But the question is, like an intuitive idea of a dialectical paraconsistent relevance logic. I think I know like a common argument for this, and it's by changing. Actually, my comment after this will be related with this. Is that usually it's because in relevance logic you change the syntactic consequence. Right?
Sure.
Yeah, that is the main point of the relevance logic. And then you may have some syntactic consequence where in the conditional, yeah, the propositions, you have propositions which are not related with the consequence. So, for example, you can have actually a contradiction there,
Yeah.
without any consequence on the consequence. So you cannot derive the theorem of non-contradiction or logical explosion. So that's why that can be a paraconsistent theory. But there is different ways to do it. That's why also there is a difference. That's why you, for example, say dialectic, because probably well, in dialectic, so far as the one I know, the J3, you can have alpha and no alpha derivable in the theory, like you can make it theorems, but you cannot have alpha and no alpha.
Yeah, sure.
Yeah. So that's like an intuitive idea of the relevance. And that's why I wanted to go to my comment. My comment will be like, that I find very nice that I like to find this, because you can think with these ideas. But so it will be interesting to do the work, in the other direction, you know, like seeing which is exactly the syntactic consequence
Right.
that you have to think about to get your order relationship.
Yeah. Yeah, sure. Yeah, that's something I thought.
Yeah, and
I think we should keep the discussion here. We thank your last comment.
That's
Thanks